Now I'm going to derive for you the work-kinetic energy theorem. I'm going to start out with two equations you already know. One, net force equals mass times acceleration. And remembering from kinematics, final velocity squared equals initial velocity squared plus 2a times delta x. Now suppose that I drop an apple. If I drop the apple, it has a force on it from gravity pointed down. And it has a displacement, also pointed down. So if I were to find the work on this apple, the work would be positive. Even if I know the apple's acceleration, I could find it from the net force equation. Right now I want to remind you that there's not a question I'm answering. I'm showing you how some equations connect, so if you don't see where this is going, don't worry yet, just watch. So I can solve my net force equation for acceleration. And I'd find that acceleration is net force over mass. Now suppose I rearrange my kinematic equation to get acceleration by itself, or the term with acceleration by itself. I'd have final velocity squared minus initial velocity squared equals 2a delta x, and that's just by subtracting initial velocity squared on both sides. Now let's take this acceleration I just found and plug it into the equation over here. So that becomes final velocity squared minus initial velocity squared equals 2 times F net over mass times delta x. Okay, the next part probably isn't going to make sense until I'm done, but now I'm going to divide both sides by 2 to get rid of this 2 over here. So divide both sides by 2. And since the 2 divided distributes to both of these, I get 1/2 v squared minus 1/2 v naught squared equals F net over m times delta x. Now suppose, to get rid of this m in the bottom, I multiply both sides of the equation by m. And that m distributes just like the dividing by 2 did. I get 1/2 mass times final velocity squared minus 1/2 mass times initial velocity squared equals F net times delta x. Now, here's what you should notice. This side of the equation, F net delta x, is net work. Over here, we have final kinetic energy and initial kinetic energy. So that would be KEF minus KEI. What that means is, since in physics we can write final minus initial using change, the net work is the change in kinetic energy. So how much ever work I do on something, that's how much I've changed its kinetic energy. And we proved it by solving right up to here. Final kinetic energy minus initial kinetic energy equals net work. So net work is change in kinetic energy. And now I'll show you a couple examples of what you can do with that. By the way, you definitely need to have all the information I just went through. Watch it again if you got confused anywhere. What I just derived is called the work-kinetic energy theorem. Work-kinetic energy theorem. And it is one of the basic facts of physics that work is change in kinetic energy. So using that fact, and I'll just rewrite it up here in the simplest form, net work equals final kinetic energy, 1/2 m v squared. And why don't I make it easier just by labeling that F, minus initial kinetic energy, 1/2 m v naught squared. Okay, so this is the work kinetic energy theorem, and I can use it to solve these two problems we've got over here. First, how much work is done on a 40 kilogram scooter to bring it up to a speed of 20 meters per second from rest? So we've got some givens here. The scooter has a mass of 40 kilograms, It has a initial velocity, if it's at rest, of 0 meters per second, and it has a final velocity of 20 meters per second. I now have all the information I need to find how much work was done to change its velocity and therefore change its kinetic energy. I can use this equation, the work-kinetic energy theorem, to find out how much work was done by just plugging in the numbers. So the net work equals 1/2 times the mass, 40 kilograms, times the final velocity squared, 20 meters per second squared, minus 1/2 times the mass, 40 kilograms, times the initial velocity, 0 squared. 0 squared is 0 times 0, so this term goes away. And then we're left with finding the net work. When I do this out, net work equals 1/2 of 40, which is 20 kilograms, times 20 squared is 400, and that'd be meters squared over seconds squared. 20 times 400 is 8,000 joules. So 8,000 joules of work were done to bring the scooter from a speed of 20 meters per second, or to a speed of 20 meters per second from rest. And that's one useful way to use the work-kinetic energy theorem, is to figure out how much work it takes to get something from one speed to another. Alright, this second example you could solve in other ways, but I can use it to show you the usefulness of the work-kinetic energy theorem. And again, that's net work equals final kinetic energy minus initial kinetic energy. A 0.2 kilogram baseball traveling at 30 meters per second moves a catcher's glove back 10 centimeters as it is brought to rest. What is the average force on the ball? So we know a few things. Mass equals 0.2 kilograms. We know the initial velocity of the ball is 30 meters per second. We know it comes to rest, so the final velocity is 0. And we know that the ball moves as it's slowing down 10 centimeters. Why don't I go ahead and convert that to meters, 0.1 meters. Okay, so I'm looking for average force. Well, I remember, just thinking about what I'll have before I know the answer to the problem, that net work is net force times displacement. So if I were to find the net work, I could then divide by displacement to get the force. I have a displacement, so now I just need the net work. Okay, here we go. I think I already have everything I need. I've got a mass, so mass check, check. I've got a initial velocity, check. I've got a final velocity. Net work equals 1/2 0.2 kilograms times final velocity 0 minus 1/2 0.2 kilograms times initial velocity. Oh, and by the way, that should have been squared even though it's 0. I shouldn't have gotten sloppy. So my final velocity was squared even though it's 0. And my initial velocity is also squared. Okay, this term here goes to 0. The negative does not go away. It's connected to the second term. So I have net work equals a negative. 1/2 times 0.2 is 0.1. And 30 squared is 900. So 0.1 times 900 would be 90 joules. So the net work is negative 90 joules. And I said earlier that once I have the net work, I divide by the displacement to get the net force, or the average force applied. And by the way, later on in the year, you're going to find out why we call it average force when we study something called impulse, because the force does not have to be constant to stop that ball. But anyway, just a preview there. We're going to get to a thing called impulse. And for now, we're just going to say average force and net force are the same thing. Later, we'll learn more about why that is. So now, I'm just dividing my network by displacement from this equation up here. If I just divide by displacement to get net force. So if we do that, the network was negative 90 joules over 0.1 meters. Negative 90 divided by 0.1 is negative 900 newtons. And if you don't believe me, it's 900. Grab a calculator or try it yourself. But the network there is negative 900 newtons. Dividing by 0.1 is the same as multiplying by 10. It's like dividing by 1 over 1/10. You multiply by the reciprocal of the fraction. So the average force applied, or the net force applied, was negative 900 newtons to bring that ball to rest. We could have also solved that problem by finding acceleration using displacement and change in velocity, and then multiplying by its mass. But you just saw another way that the work-kinetic energy theorem is useful. This last video was kind of long, but if you didn't understand anything, you need to watch it again. All this stuff is super important moving forward. Have a good night, and see you tomorrow.